In this second lecture about the great scientist Niels Bohr and his view of the atom, we get at the heart of why the periodic table takes the form that it does. Though the picture of a nucleus surrounded by electrons in circular orbits would be proven to be inadequate in describing the true properties of the electron, his fundamental reasons for the reactivity of the elements would prove to be insightful and help us move forward toward the future physics we call quantum mechanics. Bohr reasoned for ground-state atoms with more electrons than hydrogen that each atomic orbit should only hold a finite number of electrons. When a lower energy orbital shell filled with electrons, then the next higher shell would begin to fill. Now, he proposed that the orbit with the principal quantum number equal to 1 would only hold 2 electrons maximum, that the n equals 2 stationary state would hold 8 electrons at most, and the n equals 3 orbit would hold only 8 electrons. Now, later versions of the theory would place 18 electrons in this n equals 3 level, and the order of the filling of orbits would change slightly. But for now, we're going to use Bohr's simpler idea about the filling of the shells and the order by which we fill them. So let's start filling the shells with some electrons. For ground state hydrogen, the single electron goes into the n equals 1 orbit. Now helium has 2 electrons and they both can go in the n equals 1 orbit, filling it up. For lithium, we have 3 electrons, with the first 2 going in the first Bohr shell, filling it up, and the last electron we will put in the second n equals 2 shell. We continue filling this n equals 2 shell with electrons as we go to larger and larger atoms until we finally reach neon, which has 10 electrons, which fill both the n equals 1 and the n equals 2 shells completely. For sodium, which has 11 electrons, the last electron has to go in the n equals 3 orbit, and we keep going, filling the n equals 3 shell until we get to argon, which again fills Bohr's n equals 1, 2, and 3 orbital shells. Now, do you see what we're reproducing here? We are beginning to look like the periodic table. Bohr had discovered the secret to the periodic nature of the elements, and a clue to the nature of their reactivity. The electronic structure of elements determines the reactivity of the elements. What makes alkali metals similar in their chemical reactivity? Well, the answer is that they each have a single electron in their outer Bohr orbit. Why do these elements tend to be cations with a single positive charge? Well, remember my Striplin law that everybody wants to be noble? Well, if these elements get rid of that pesky 1 electron, then they have filled shells just like the noble gases. So why are they so reactive? They just need to shed 1 electron to be happy, so they eagerly look for anything they can give that electron to. So it follows that we can now address the question, why are noble gases so inert? Well, they have filled shells, and that must be one of the important goals of atoms if they want to be stable and unreactive. So if you have a full set of orbitals and no residual electrons, you must be pretty stable and happy. What makes halogens similar in their very robust reactivity? Well, they all lack just 1 single electron from having a full set of orbitals. That's also why they typically are anions with a single negative charge. And since they are just 1 electron away from happiness and being noble, they are quite willing to give that electron up to anyone who'll take it. So it shouldn't be a surprise to us that you will often find these elements hanging out with alkali metals, which are more than willing to give them the electron they desire. So opposites do truly attract each other, I guess. When we look at the periodic table, we find the most reactive, naturally occurring elements located at the bottom left corner of the table, Cs, cesium, and the top right of the table at F, fluorine. Bohr's atom seems to give us insight into why these atoms form the most reactive centers. Cesium would have a single electron in its outer shell, just like the rest of the alkali metals. Thus, it's already eager to get rid of the electron in the reaction anyway. But in cesium's case, this outer electron is so very far from the nucleus, and the pool of the nucleus is shielded by a great many other negatively charged electrons, making it that much easier to donate that electron to some other unsuspecting atom. Large atoms that want to give up electrons to be cations tend to be more reactive than smaller ones. The opposite is true for atoms that want to be anions. They need that nucleus to be close and relatively unobstructed by other electrons to help lure the extra electrons to them. Fluorine needs just one more electron, and the shell it wants to fill is relatively close to the nucleus. This lethal combination of driving forces makes fluorine extremely dangerous to be around. Smaller atoms that want to be anions tend to be more reactive. So because the outer electrons in the outer orbits are so important to the reactivity of the atom, these outer electrons became known as the valence electrons. Let's quickly review the big ideas and discoveries that Bohr gave to us to help us understand the nature of the atom. Bohr discovered why matter generates distinctive emission and absorption spectra. Electrons are confined to orbits, and when they are excited in an absorption process, they move to higher energy orbits. And when they emit light, they are moving from these higher energy orbits back to lower energy ones. The orbital system about each atom of an element is unique, and the orbits are quantized having distinctive energies, so the absorption and emission spectra are unique to that matter, identifying their unique fingerprint. Bohr discovered the principal quantum number of atomic orbitals. This number represents the energy and the distance from the nucleus of electrons that might reside in that orbit. Bohr discovered that the electronic structure is the key to why atoms behave the way they do, and that the number of valence electrons, the electrons in the outer orbits, was the key to the periodic nature of the periodic table. Now, he also gave us quite a few wonderful quotations. Read these on the slide and enjoy. As we said before, Bohr's picture of the atom is now known to be rigorously flawed. But in no way does this diminish the tremendous insight he gave us into the very nature of elements, matter, and chemistry. Now we're ready to look at the fundamental theory we now use in understanding the atom, quantum mechanics. So I'll catch you later.